Alright, enough yapping about friends who took away my soul and poorly made life choices and social anxiety and depression. Let's talk about fluorescence. Fluorescence is a really cool phenomenon when a molecule gets excited when incident light or specific wavelength falls on it and the electron jumps from a lower energy level to a higher energy level. It is a bit more complicated than that because it is quantum mechanics, but the gist of things is electron jumps from a lower energy level to a higher energy level because of absorbing the incident light source and then jumps back down to the lower energy level, thereby emitting energy in the form of a photon of a specific wavelength that we see as a light being emitted from that molecule that we call fluorescence. It's like the cell phone stand that I have here. This flappy thing, let's imagine this is the electron and the stable states the flappy thing sits in are the energy levels. Let's just assume that for a minute. So this electron can exist anywhere in these states, but it only sits at a specific equilibrium place like this. Even when I leave it in between these energy states, it just sits somewhere in the existing equilibrium levels. Let's see fluorescence in this analogy. When you put the exact energy needed for this electron to jump from one state to another higher energy state, it goes like this, right? So I put in just enough energy for this flap to go from one state to a higher energy state, right? Because I put energy into it. This is when the electron makes the transition from a lower energy state to a higher energy state in the presence of a specific wavelength incident light. Then the electron won't stay there forever, right? So it comes back down to the original lower energy state. When that happens, it releases energy, the exact energy I put into it, right? So that released energy comes in the form of a photon of a specific wavelength, and that's how fluorescence works. Now let's learn about fluorescence using this, a Jablonski diagram. A Jablonski diagram is just a representative diagram explaining fluorescence and phosphorescence in disgustingly minute detail. This S0 and S1 represent different energy states, and you can see this energy state is much lower than this energy state in terms of energy. Like this. Energy keeps increasing in this direction. And this gap of energy represents the incident light energy that falls on here and enables the electron to make a transition from this energy state to that energy state. And these individual energy levels are the vibrational states that exist within an energy state. Now you may ask, why are these energy states represented by S? What is the meaning of S here? S represents a singlet state. A singlet state occurs when an electron makes a transition from here to here without changing its spin. What is a spin, you may ask? It's just a characteristic property of an electron. We assign it plus half or minus half if it spins in the clockwise or the anti-clockwise direction, and so on and so forth. The mathematics behind the spin of an electron is very, very complicated, but the thing is, Pauli's exclusion principle, which states that two electrons sitting in one orbital cannot have the same spin, it single-handedly defined chemistry. I am not over-exaggerating. That's the main principle behind the formation of chemical bonds, which is chemistry. Now, an electron can make a transition from here, like this, or to there, or to there, or to there, and so on and so forth, right? Now you may ask, why can't electrons jump from here or here or here to here to the higher energy level? It can, obviously it can, but we don't write it in the Jablonski diagram. Why? Because it doesn't result in appreciable quantum yield of light when an electron goes from here. This observation is called Kasha's rule, and this Kasha's rule has a significant impact on fluorescence. Why? Because it states that only those electrons that jump from the lowest energy level of a given multiplicity, given state, only those can yield appreciable levels of light. Now, you might have a doubt. If these electrons come back down to the original lower energy state, won't it release the same energy as the incident light? That's a good question. But we don't see that. When we use blue light, we only see green fluorescence or yellow fluorescence. It releases light that's of less energy than that of the incident light. Where does the extra energy go? Like here, we can't see other places where the energy can go, right? Where does it go then? Now, remember Kasha's rule. Only when an electron jumps from the lowest energy level, fluorescence can be easily observed, right? So these electrons which are at the top of the level must come down to this state right here, because this is the lowest energy level of the given multiplicity, right? So this should come, all these electrons should go here and then make the transition like this. Now, to make this transition, the electrons, let's denote it by this curly arrows. This process where the electrons go within that energy state, just relax to a lowest energy level of the given multiplicity, is called internal conversion. Now, all these states are equilibrium states. So for an electron to jump from this equilibrium state to that equilibrium state, it requires energy. So this is where some part of the incident light energy goes. So this process is endothermic, so as to speak. It requires energy to make the process happen. So this internal conversion happens to obey Kasha's rule and then makes the transition, thereby emitting energy that is less in terms of energy when compared to the incident light. Now this is a pretty huge rule when it comes to fluorescence, an empirical rule, so as to speak. When I use incident light of say h nu energy, the emitted light of say energy h nu dash, that energy will always be less when compared to the incident light. Now this is very important. As you can see, when I use my blue light, we only see green fluorescence or yellow fluorescence or orange fluorescence and so on and so forth. But you can't see blue fluorescence because this process needs to happen so that it can obey Kasha's rule, and this process requires energy, right? So it takes the energy from the incident light energy, right? So the emitted light always has less energy compared to the incident light. But we do see blue fluorescence though. In terms of anthracene, which has blue fluorescence, you have to hit it with not blue light but UV light, which has more energy when compared to the blue fluorescence it has. But another question still remains. Why does these two similarly colored objects behave stupidly differently under this blue light? See, this cover that was once yellow appears black to my eyes, but this another yellow colored toy like stuff appears yellow fluorescent. The answer lies in the fact that one deals with absorption of light by the molecule as a whole, while the other deals with absorption of light by the electron. They might sound very similar, but they are stupidly different. So fluorescence is really neat, and it encompasses all the basic stuff there is to learn in quantum mechanics. Pauli's exclusion principle, electrons making a transition, light quanta, and all that kind of neat stuff. It's pretty cool. And I'll also look extremely possessed under a blue light. So it is very cool. And the video has officially come to a conclusion. If you want to see more of these videos, please subscribe to my channel and I will make more of these because these are extremely fun to make. I'll keep making these videos only if you subscribe. I think I broke the sensor. And with that, we will conclude this video. Thank you for watching. Bye.